So here's another example from section 15.3. This is number 22. This one's a little more interesting. As I said in 19, and then at the beginning of 15, the chapter, we said the first thing we want to do is try to identify the region, or let's see, where am I trying to integrate over, and which one's the surface. This one's a little more difficult because I don't have, it doesn't just tell me this is my function and this is my region. We have to think about it a little bit. So if I think about the sphere, I have a sphere here. I want to know what's the volume inside the sphere, but outside of a cylinder. So if I have a sphere with the center, like the hole drilled through the middle of it, that's what I'm trying to find the volume of. The sphere minus the inside part, the shaft. So to find the region, what I want to do is I want to take projections of these two shapes and see what do they land on the XY plane. So here, if I project this onto the XY plane, that's going to give me a circle of radius 4, right? And then this, the cylinder, is just going to give me a circle of radius 2. So if I talk about my region of integration, so that's with the radius of 4, and then this inside one here has a radius of 2. So I want to integrate over what looks like this donut or a slice of pineapple with a core taken out. So this would be very difficult to do in rectangular coordinates. I don't want to have to think about going from the square root of something to a different square root and then a square root to another square root and breaking it up between the top half of the circle and the bottom half of the circle. But what I can do is if I write this in polar, that just means that my radius is going to go from 2 to 4. So all my radiuses are from 2 to 4. And then my angle, I'm going to go all the way around the circle. So theta is going to go from 0 to 2 pi. That'll give me that region around the outside with the hole taken out for the middle. So now I need to decide where my surface is. So if I think about this as a sphere with the center taken out, I'm actually gonna, if I take a slice of this, that's my sphere with the center taken out. So this is in 3 dimensions, right? So this is being spun around this way. I'm actually using this is gonna end up being my surface. And the reason why I'm only drawing it down and I'm not going into the negative values is that I'm gonna take, if I take just positives, I can integrate and I can multiply it times 2 because the bottom half, the volume on the bottom half is gonna be the same as the volume on the top half. So that's why I have this 2 out on the front of the integral, is because when I integrate, I'm just gonna find the top hemisphere and then I'll multiply it times 2 and that'll give me the total volume. So this is again for my theta, let me label that. This is for my radius, it's gonna go from 2 to 4. Now I need to think about the function that I'm plugging into the inside. Well, let's see, we said this surface, the sphere, is my surface that's bounding me. So that means I have, let's write this as a function of x and y. So I need to get this to be z equals. So I'm going to subtract these 2 to the other side. And by square root, so I went out and I factored out a negative out of both of these because this helps me, since I've decided I'm going to do this in polar, I know that x squared plus y squared, that is r squared. So when I square root here to solve, this should have a plus or a minus. But instead of having to deal with both of those, what I'm going to do is I'm just going to take the positive part up here I'll find this, and then I'm going to multiply it by 2 to get the total volume that's created. So this is my function of x's and y's. So to write this as a function of r's and thetas, I'm going to have the square root of 16 minus r squared. Remember my r, don't forget that. Let me clean this up a little bit. Some space to work. So now I'm going to break this apart the same way that I broke up the integral from last time. I'm going to write this as 2 times the integral from 0 to 2 pi d theta. Because here, this only has r's in it. I don't have to worry about this. Since this is only r's, when I do that integral, it's just going to become a coefficient for the second integral. So I get those 2 integrals. I simplify. This is going to be 2 times 2 pi. Let's see what happens here. I'm going to do a u substitution. So that u substitution gives me what I want. I can replace this. So that's going to be the integral of -1/2 u to the 1/2 du. That's going to give me -1/2 times 2/3 16 minus r squared to the 3/2. I want to evaluate that between 2 and 4. So if I notice -1/3 16 minus 4 squared plus 1/3 16 minus 2 squared. This is 0. This is going to be 1/3 12 to the 3/2. So let me write that. Let's do a little work with that. 12 is going to be 2 cube root of 3, or square root of 3 to the 3rd. So that's 2, 4, 8. So I have 4 times 8 is 32 pi square root of 3. So that tells me the volume inside a sphere of radius 4, but still outside a cylinder of radius 2. Again, let me say, if you have questions, if you need help with anything, if you're not sure about any of the steps that I did, or if you're not sure about any of the content or anything from this section, go ahead and post in the discussion board. I'll make sure to check in on those on a regular basis and answer any questions or posts, or if you recommend some more videos or something, or some notes written out, just let me know what you need, and I'll do whatever I can to make it happen. Cool. Thank you.